Hi everyone, this is Mr. Chu. I'm going to go through topic 9.5, which is on Doppler effect right now. So Doppler effect is the shift in frequency when the source of the observer is moving. The technical definition is that Doppler effect is the change in the apparent frequency or effective frequency when there is or due to the relative movement between the observer and the source. So Doppler effect is basically the change in frequency of the usually sound. In our syllabus we talk about sound more often, and due to the movement, the relative movement between the source and the observer. So let's talk about the moving source first. So if we have a source that is emitting sound, if it is not moving, the sound waves moves out like this. Alright, so between here is the lambda and this is the lambda. Every wavefront, successive wavefront, the distance between them is one wavelength. Now, if you have a source moving towards the right, this is what happens. When one period has passed after the first pulse is produced, this is one wavelength. However, what the source does is that it moves forward towards the right. Say, for example, if it moves forward at the speed of v source. During that time where this wavefront moves out, this source moves towards the right. So at the point of time where it produces the next pulse, it will be somewhere around here. It is slightly towards the right. Therefore, when it produces the next pulse, and after one more period, it will look something like this. So the distance over here is actually being reduced. And this lambda effective is actually equals to the original wavelength minus the distance that the source travels through in one period. So that's the effective wavelength. Something noteworthy for you to know is that when source is moving, the speed of sound is unchanged. This is important because IB loves to ask this, whereas the wavelength is changed apparently, as you can see over here. Now, how does this lead us on to the equation for Doppler effect? Let's take a look. So the speed of sound is unchanged, so V of sound over frequency effective. This is lambda effective because speed of sound no change. This is F effective, therefore this will give you lambda effective. This is lambda original, so it is speed of sound divided by frequency original minus speed of sound, speed of source, sorry. This is 1 upon frequency original because the period depends on the original frequency. It is not dependent on any motion. The frequency of the pulses being sent out doesn't depend on the source frequency or the source speed. Therefore, if we were to rearrange or rather we factorize this will be 1 upon frequency original V source, V sound minus V source over here. And if we were to rearrange, this will give us F effective equals to F naught times V of sound over V of sound minus V of source. So as you can see, this is a minus, and when you take this divided by this is going to be bigger than 1. And therefore, the frequency received at this point, if the observer is just standing still, is going to be bigger than the original frequency. And I hope it is not difficult for you to deduce that on the other side over here, this will be a plus because the wavelength is being elongated. So this is the case where the source is moving. If it is moving towards the observer, you choose a negative sign to increase the frequency. And when it's moving away from the observer, you choose a plus sign, which reduces the frequency. So what happens if the observer is moving? I'd like you to think about this. If the observer is moving, what is changed? And what is unchanged? Now, if I have a source producing waves traveling towards the observer at the speed of sound, and I got an observer moving towards the sound at speed V observer, can you see that the speed of sound, or rather the effective speed of sound, is changed now, because now instead of V of sound, it has become V of sound plus V of observer. But the wavelength is unchanged. Because the wavelength, if you're to freeze at any point of time, it is not like the previous case where the wavelength is literally changed. But now, if you freeze at any point of time, you still measure lambda over here. So the wavelength is unchanged. You must remember that for an observer moving, for the case of an observer moving, the speed of sound is changed. Not that the speed of sound is changed, but the effective speed of sound is changed because of the relative motion. So instead of this one, it is now this one. And the wavelength is unchanged. So let's take a look at what's the effect. So for this case, you have the situation where the V is equals to F lambda still. Now this is F effective, lambda is unchanged, and this has become V of, probably I'll create some more space on this side. So this has become V of sound plus V of observer equals to frequency times lambda, and wavelength is the original speed of sound divided by F naught. And this is your F effective now. So F effective is now equals to F naught if you rearrange V of sound plus V of observer divided by V of sound. So I can see the effect of observer is in the numerator, whereas the effect of source is in the denominator. And because the observer is moving towards the source, it experiences more wave fronts per second. Therefore, it is a plus. If it is moving away from the source, then it will be a minus. Now, it is not difficult, I hope, for you to imagine that if I got both moving observer and moving source, then it will be V of sound plus minus V of observer divided by V of sound minus plus V of source. So how do I know which one to choose, plus or minus? Let's use some examples to consolidate, all right? That's the key. I mean, knowing the equation is one thing, knowing what sign to use, that's also key. So let's go through some examples and it becomes clearer. So this is source, this is observer. Now let's go for the case where both of them are approaching each other, and then the case where both of them are receding from each other, and the case where the source is chasing the observer. All right, so this should be it. If it is not enough, we'll go through more cases. So for this one, it will be F naught V of sound. V of sound, we know that this is V of observer, V of source. Now remember, whenever the source is going towards the observer, it will increase the frequency. The effect is increasing the frequency, so it choose minus. Whenever the observer is moving towards the source, it increases the frequency, so this should be plus. All right, so let's take away those terms, and then let's talk about the sign over here, because everything, these four terms over here will still be here, and this term will still be here. And so for the top, the observer is moving away from the source. We don't care whether the source is moving towards the observer or not. Once the observer is moving away from the source, we choose a negative sign. It reduces the frequency. And the effect of source is at the denominator. So when the source is moving away, it decreases the frequency. So you choose a plus. And then next one, here. If the source is moving towards the observer, the effect is increasing the frequency, so you choose a minus because source is at the bottom. And the observer moving away from the source, and therefore the effect is lowering the frequency, so you choose a minus. Not difficult for us to imagine that if both goes this way, then you'll be plus plus. All right, so choose the sign according to whether the observer or the source is moving towards the other party. Okay, so hopefully this will clarify some of the situations that you need to handle as to when to choose plus, when to choose minus. Now, the other case that IB loves to ask, let's start off with the graphical questions. Then we will go to some of the sample questions, and then we'll call it a day. So let's take a look at the situation where you've got source moving towards an observer and pass, and the source move past the observer at time t equals to t naught over here. So this is the frequency effective, this is the original frequency. Now one of the most common wrong answers that students will give is something like this. Why? Because some students have this idea that when the source gets nearer and nearer, the frequency gets higher and higher. It's actually not true. If you look at the equation, F effective equals to F naught V of sound over V of sound when it is approaching is V of source. There's no part in this equation that depends on distance. So if the v of source is constant, then it should be a constant and it shouldn't change. And when it's moving away, it is moving away the same speed, so it will be plus over here. So this applies for this. When it's over here, it will be f naught v of sound over v of sound plus vs. So it'll be a constant value that is lower. The reason why it seems as though it's getting higher and higher is because probably because it's getting nearer and nearer, the effect gets more and more pronounced. That's why we think that it is getting sharper and sharper. But please remember that it is like this. And of course, some students will argue saying that who would be stupid enough to place the head in the line of the car? Of course, we are assuming that the head is close enough to the car so that the speed over here is the speed of the source. Now, there is a situation where if you are here and the source is here, so there is a certain angle that you make with the source. Now, then what you need to do is to resolve this one. It will be Vs cosine theta, that is the one that you should plug into this equation. So you must use the velocity that is along the line of the source and the observer. But of course, if we are assuming that the head is close to the line of the travel, then theta is small enough for us to not consider this effect. Okay, so let's do one question, mathematical question, with regards to the use of the numerical use of the equation. Let's jump into the deep end of the pool and do a rather difficult question that requires two unknowns and two equations. So also this example, let's build on this and give it some numbers. And in region A and region B, the person hears a frequency of 2005 Hertz. And in region B, the person hears a frequency of 2000 Hertz. And the speed of sound is equals to, let's make it simple, 300 meters per second. So your task is to find F naught and the V source. So let's take a look at the numbers given. Obviously, we need two equations because there are two unknowns. So 2005 is equals to F naught, which is unknown, divided by, multiplied by the V of sound, which is 300, divided by V of sound minus V of source. And this 2000, which is on the right side, the source is moving away, so I should choose a sign that decreases the frequency. So it should look like this. Now, one of the ways to solve this, probably can find a faster way. One of the ways to do this is to divide the equation, and then this goes away, this goes into 5 upon 4, this goes away, and this will become 300 plus Vs over 300 minus Vs. And then if you cross multiply, it will be 1005 minus 5 Vs equals to 1002 plus 4 Vs, and you'll find that Vs9 is equals to 300 and Vs is equals to 100 divided by 3, which is 33.3 meters per second. And then plug it back into any of the equation, you're going to get the equation, the value for F naught. So this is how you can handle this kind of question. All right. Now, something that is also quite difficult and something that it will give some trouble to you is this kind of problem that involves reflection. Now, I'm going to give you the most difficult case. All right. There are some permutations, but this is the most difficult that you as an IB student, you encounter. Let's call this X and Y. X produces a sound. This is Vx. This is Vy. Now, Vx produces a sound, bounces off y, and then comes back to X. So the task for you is, given that the original frequency, the proper frequency when everything is at rest is 2000 Hertz, and this is 30 meters per second, and this is 15 meters per second. So what's the frequency that X is going to receive back at when it bounces off Y? So to do this, you always find the F effective when Y receives the frequency. So for this, you've got 2000 over here, multiplied by, say, the speed of sound is again 300. It should be given to you. So V of sound is equals to 300 meters per second. So you've got 300, check. Let's write 300 first. And we know that this is 15 and this is 30. So leave it first. Then you check the sign. So worry one thing at a time. Don't worry too many things. So just write in the numbers, then decide the sign. Because this is definitely correct, the order. And then the top is the observer moving away or towards. It is moving away. So you choose a minus to reduce the frequency. Is the source moving towards the observer? Yes, it is moving. So it should increase the frequency, and therefore you choose minus. So if you work this out, this is 2000 times 285 divided by 270, and you should get a frequency of 285 divided by 270 times 2000. That will give you 2111 Hertz. So that's the frequency received by Y. Now Y is a observer and X is the source. However, when Y reflects the sound, guess what Y becomes? Yes, Y becomes the source because Y is now emitting the sound back at X. So now Y takes the position or the role of a source. So you have to be very careful over here. So when Y reflects the sound back, F2, which is the frequency received by X, with X being the observer now. So to make that clear, X is now the observer. So this is 30, this is 15. So the source, which is Y now, moves backwards at 15 meters per second, whereas the observer, which is X, is moving at 30. Now let's take a look at the situation now. The source is moving away from the observer, so it decreases the frequency, so you choose plus. The observer, which is X, is moving towards the source, which is Y now, throwing the sound back at X, so it increases the frequency. Therefore, you choose plus. So this becomes 330 divided by 315 times, oh, this is not 2000, sorry, it is 2111, because the frequency that Y throws back at X is 2111. And this will give you 2210 to 3SF. So that's how you handle two objects moving, and you're throwing sound at one, and then it reflects off to the other party. It can be a different combination. It can be X moving towards Y, Y moving towards X, or X moving away from Y, Y moving towards X, or moving away from each other. It can be different combination, but the method is always you must treat the other party as the observer first, and then when it throws the sound back, it changes role. The object over here, the car over here, becomes the source. So that's the thing you need to understand and remember. One last thing before I end off Doppler effect is this thing. Actually, there are two more things. Second last thing is if I got the wind blowing towards from a source, this is the source to the observer. If there's a wind bringing the sound blowing from here to here, does it change the frequency? Probably give yourself pause the video here and think, is it going to increase, decrease, or the same? So let's take a look and see what's the effect. Yeah. So when the sound is moving from here to here, the wind moves from here to here because the wind carries the air, so it actually increases the speed of sound. So the speed of sound goes to become speed of sound plus speed of wind. And because the wave is being brought forward by the wind as well, so the wavelength original becomes wavelength original plus the v of wind times the period. It's almost like the wind carrying the wavefront a further distance away. Because of the air moving. So therefore, let's take a look at V equals to F lambda. F effective is equals to V effective, which is V of sound, plus V of wind divided by lambda effective, which is lambda naught, plus V W times T, which is equals to V of sound plus V of W divided by V of sound divided by F naught plus V of wind divided by F naught. Why? Because period is 1 upon frequency. Lambda original is speed of sound divided by frequency original. Now if you factorize or bring this up, F effective is equals to V of sound plus V of wind divided by V of sound plus V of wind divided by F naught. You should be able to see by now that this is equals to F naught. So what am I trying to say? Basically what I'm trying to say is that if you got a wind, whichever way it blows, it doesn't change the frequency. Otherwise, it'll become really weird. I mean, if you talk in the wind, you're going to sound different. We don't experience that in real life. All right. So wind doesn't affect the frequency. Okay. Now, one last thing, as promised, that we need to go through is when you talk about light. So when you talk about light, this is what happens. So let's consider the case where the source observer, say the observer moved towards the source. So the F effective is equals to V, if you talk about light, F naught, this will be C, which is the speed of light, plus the V of observer divided by the speed of light. So this is going to be F naught 1 plus V naught upon C, and F effective minus F naught is equals to F naught divided by F naught times V upon C. I'll just open up and then brought F naught over. So delta F upon F naught is equals to V upon C. Now this is something you need to remember when we talk about light waves. This is the equation we use. But of course, we're talking about low speed. If you talk about really high speed, then you need to use the relativistic Doppler effect, which is different from this case. So we're talking about low speed. You can use this approximation that the change in frequency divided by the original frequency is equals to the speed of the observer. It can be the source of the observer. You can use the same formula and divided by the speed of light. All right. So that is something that I'd like to go through with you for light. And most of the things we went through is for sound. Okay. So just a quick recap. Very important stuff. Be able to define Doppler effect. Remember that when the source is moving, you change the, you don't change the speed of sound, you change the wavelength. When the observer is moving, you change the speed of sound. The effective speed of sound gets changed and the wavelength doesn't get changed. But of course, if you have a wind, as we've proven just now, it doesn't change anything. Now, the next very important thing is you need to know how to choose the sign. Whenever one, be it the source or the observer, is moving towards the other party, you choose the sign that will increase the frequency. Whenever the source or the observer is moving away from the other party, then you choose the sign that decreases the frequency. So one way is I always put in the numbers first, the plus minus, I'll leave it to the last because you need to consider it carefully. Most of the time, the problem is with the sign, not with the plugging, because the equation is given in the data booklet. All right, so be careful. It is quite a fun topic. It is really quite interesting and not a very difficult topic. All right, hope you like it. Thank you.